Okay, so now let me try to write the infinitesimal heat exchanged in a reversible process explicitly as a function of the variables of state in a specific physical system. Okay, so what I want to do is to somehow get an expression for this heat when I'm doing an infinitesimal reversible process. Okay, so let's see how we can do that. And to do that, first thing we have to do is to specify a physical system. Okay, and as usual, we are always going to work, or almost always going to work, with a single component expansive system characterized by volume, pressure, and temperature. And the number of moles, I'm going to choose it to be 1 mole in all this video. Okay. So we know that the function of state will constrain two of these variables and leave only two independent ones. Okay. So this means, in particular, that I can choose volume and temperature as the independent ones, and then always get pressure out of the equation of state. So if I do that, let me just write the differential of u, which is, I will specify a function of v and t. And applying the chain rule here, I just get that this is a partial derivative of the internal energy with respect to volume at constant temperature, differential of b, plus the partial derivative of u with respect to temperature at constant volume, differential of t. So also I want to emphasize this notation. In thermodynamics, every time we write a partial derivative, we're going to write it like this. The partial derivative of whatever we are differentiating with respect to the variable that we are differentiating with respect to, and we specify always which other variable or variables are left unchanged as a sub-index in parentheses, like you can see there. Okay, fine. So this is, if you like, the left-hand side of this expression. Let me just explicitly write it. And what we want to get is this q. Okay, so of course you know that the left-hand side of this expression, the differential of u, is a differential on a variable on a function of state. Sorry, yeah. And because of that, the differential is independent on which specific path you choose to take from the two infinitesimally close neighboring equilibrium states that you're thinking of. Yeah. So in particular, you can choose to go from these two infinitesimally close states doing a reversible process. Okay, so if you do a reversible process in an expansive system, we know what that is. We know what is the reversible expansive work. And this is going to be nothing but minus p dv. Okay, and now we have what we wanted, because we wanted to write differential of q, the reversible infinitesimal heat in an infinitesimal process, which is reversible, as only a function of the variables of state of my system. And we can just do this from this expression. From here we get that differential of q equals, and we put this minus p dv to the other side of the equality. So we end up having the partial derivative of u with respect to v at constant temperature plus the pressure, and the common factor here is dv, plus the partial derivative of u with respect to t at constant volume dt. Okay, so this is what we were after. That's the final expression I wanted. Okay, we are going to come back to this. Let me highlight it in different color. We are going to come back to this in this video later, but also in the course we are going to come back to this expression several times. And we can get a different expression in terms of different variables of state if we just choose a different set of independent variables from the beginning of the problem. Okay, so imagine now in the beginning we choose, instead of volume and temperature, we choose pressure and temperature. What would happen then? Okay, let's do the derivation in that case. Again, I know from the beginning that differential of u equals the work, reversible, plus the q, reversible, and this is minus p dv plus dq. Okay, so in the reversible case, now I emphasize this once more. I'm free to choose any breakdown of the total change in internal energy that I want. So I'm just choosing reversible processes because I am interested in the reversible heat in the first place, and also because I know what the expression for delta work is in a reversible infinitesimal process. That's all, okay? And I could choose anything else, and the addition of any other work and any other heat is always going to sum up to the total differential of internal energy, okay? Well, let's just choose, like I said, pressure and temperature as independent variables, okay? So pressure and temperature, this is again going to be the partial of U with respect to P at constant T, differential of P, plus the partial derivative of U with respect to T at constant P, differential of T, okay? And this is equal to that, to minus P dV plus delta Q. However, I have dV here, but my independent variables are P and T. So what I have to do is to write dV in my independent variables, okay? I want to write this as a function of P and T. Everything has to be written as a function of P and T only, okay? So how do we do that? Well, we just do the chain rule again. The volume is related to the pressure and temperature through the equation of state, which means I can calculate what this differential is by taking the corresponding partial derivatives from the equation of state. In this case, this is going to be the partial with respect to P at T constant, differential of P, plus the partial of V with respect to T at P constant, differential of T. Okay? And we have to plug that in this expression here. So let's collect everything together. We have on the left hand side the partial derivative of U with respect to P at constant T. I'm just copying from here, from this line, right? So let me just copy that. With respect to T, P, differential of T, and this is going to be equal to minus P, and this multiplies the partial derivative of B with respect to P at constant temperature, differential of P, now I'm copying from this line, plus the partial derivative of B with respect to T at constant P dt. Okay, going to try to make this a little bit smaller so that everything fits in the screen like that. Okay, fine. And this goes plus the infinitesimal reversible work that I want. So now, again, I can collect everything together in the left-hand side of this expression, which finally gives me, well, what is it? A partial derivative of P with respect to T, plus P partial derivative of V with respect to P at constant T, differential of P. Okay, and then the other term that goes proportional to differential of T, which is the partial derivative of U with respect to T at constant P, plus P partial derivative of P with respect to T at constant P, everything times differential of T. This is the second expression for the infinitesimal reversible heat exchange in an expansive system doing a, let's say, infinitesimal reversible process, okay? So, okay, fine, that's an expression for now. I will copy as well here the other expression that we have derived, just to have them the two together. Okay, this is not what I want to do. I want to come down here, and I want to somehow paste it. There you go. Okay, so here you have the two of them. So here you can see that there are some interesting partial derivatives, okay? In particular, I called your attention on this one and on that one, okay? So these ones are appearing everywhere when you are dealing with expansive systems, and they have a special name, okay? So the first one is the coefficient of thermal expansion, and this is defined as, okay, so it's coefficient of thermal expansion. Let's try to make sense of the words to help you remember. Coefficient of thermal expansion. Thermal expansion. So what's that? What does that sound like? Well, to me, that sounds like the change in the volume when you change the temperature. So how much you expand as you increase infinitesimally the temperature at constant pressure, okay? And usually you want to normalize this by the total volume, because this derivative will depend on the total volume and you want to have it independent of that. And you give it a name, and this name is alpha, coefficient of thermal expansion. Okay, so alpha is appearing here, right? And then we can also define the isothermal compressibility. Let me just, yes, that's the name. Isothermal compressibility. Or just compressibility. Okay, and this is defined like this. So this is the change in the volume, yes, as you change the pressure on your system at constant temperature. That's isothermal compressibility. And usually you know by experience that what happens when you apply pressure on something, the volume shrinks. So when the increment in pressure is positive, the increment in volume is negative. So generally speaking, this derivative you expect it to be negative. So because we want positive coefficients, we put a minus sign, and also we normalize by the total volume as it's our custom. And this we are going to call Vita. In the literature, there's also different notations for these things. Don't want to confuse you by that, but I just want to mention, just in case you are checking any of the books in the reading list and you are confused. So this one is actually sometimes called Vita, which is very confusing because this is Vita. Don't be confused by that. Just always look at the name, coefficient of thermal expansion. Now this one is most often called beta, but it can also be called capital KT or lowercase kappa t. Okay, but like I say, the most common names are alpha and beta. These are the ones that we are going to use in this course. Okay, and now let me finally, to conclude this video, introduce two more coefficients, which are the heat capacities, or in our case the molar heat capacities at constant pressure and constant temperature. So the heat capacity at constant pressure is simply the reversible heat, okay, per unit temperature. So the reversible heat that the system has to absorb to raise its temperature infinitesimally by delta T, when the process of absorbing this heat is happening at constant pressure. And I emphasize that this heat here is reversible infinitesimal heat, okay? Fine. So that's the definition. And then the heat capacity at constant volume is the reversible heat absorbed by a system to raise its temperature infinitesimally by delta T when the whole process is made keeping the volume constant. Okay, so fine, this is just definitions, but we can actually say something about these definitions using the two expressions that we derived before. Okay, so here, for instance, here we have the reversible heat. Okay, that's what goes in the numerator of these two expressions. Now, when the pressure is constant, differential of pressure is zero. So where do I have differential of pressure in these two expressions? In the first one. So it means that this differential of pressure is zero in a constant pressure process, which means delta Q equals partial of U with respect to Tp plus P partial of B delta T, differential of T. If I divide by differential of T, this differential of T disappears. So what I say is that I can write the heat capacity at constant pressure as these two terms here. So this is, as usual, not what I wanted to do. So let me paste here. Okay, so that object there is, well, that doesn't look very nice, actually. That's partial of V with respect to T at constant P. Okay, so this is the heat capacity at constant pressure. And the same thing can be done about the heat capacity at constant volume. For this, we go to the other expression we have here. Constant volume means this goes to zero. The reversible heat divided by delta T equals simply the partial derivative of the internal energy with respect to temperature at constant volume. Okay, so let's just write that. Partial derivative of internal energy with respect to temperature at constant volume. Okay.